So what we have here is a circle. I'm going to draw a radius here. And if I took this beautiful triangle to make that circle. Anybody know what kind of triangle this is? What's the name of this triangle? It's isosceles because it has two sides that are the same. It's even got a special because it doesn't matter which one. What is it called when all three are the same? Remember? Special isosceles. Starts with an E. Equilateral, yes. So an equilateral triangle has all three sides the same. Do you know what the angles of all three are on this equilateral triangle? Has to add up to 180. They'd all be 60, right? So if I took this equilateral triangle and I bent it, if I pushed down a little bit, can you see that the one side would bend? And if I did it perfectly, so that I bent it so that that arc length was exactly the same as the radius, then would you agree that this angle right here would be a little bit less than 60 degrees? Okay? In radians, that's exactly 1 radian. When the arc length is exactly the same as the radius, you have 1 radian. And as an estimate right now, we could say that 1 radian, just by that pushing down on this triangle, because as I push down, this angle would get a little bit smaller. This equilateral triangle where every angle is 60, as I push it down, this angle is a little bit less than 60. Okay? That would be 1 radian. So as opposed to degrees, which someone decided there are 360 degrees in a circle. But it's just an arbitrary number. A radian is actually based on a measurement. If the radius, the arc length of the circle, is the same as the radius, you have 1 radian. So if we go along here, say there'd be 1 there, I can make another radius there, another radius there, another radius, another radius, another radius. 1, 2, 3, 4, 5, 6, and there's a little bit left over. Question is, how many radians are there in a complete circle? Well, what am I counting if I'm going around the edge of the circle? Just like we did yesterday or the day before. What is that called when you go all the way around a circle? That's your circumference. What is your circumference formula? It's 2 pi r. I'm going to put that r in brackets right now. Normally you don't. But right now I'm going to put it in brackets because if you think about what that formula means, that formula means that around the edge of our circle there are 2 pi radiuses. 2 times pi, 2 times 3.14 is about 6.28. My diagram showed 6 radiuses and a bit more, 6.28, or 2 pi radiuses around the outside edge of the circle. And if every time you have a radius on the outside edge of the circle, it's 1 radian, does it make sense that there are 2 pi radians in a circle? So a radian is just really relating an angle measurement to an arc length. And it doesn't matter how big or how small the circle is, your circumference formula is always the same. And so the amount of radians are always going to be the same. Well, this is going to allow us to figure out what 1 radian is exactly. Because now, if we just sort of make a chart here of what we know for radians and degrees, we know that there are 2 pi radians in a circle, and we know that there are 360 degrees in a circle. If you did half a circle, how many degrees would it be? 180. If you did half a circle, how many radians would it be? If you're 2 pi in the whole one, in radians, it would be pi. I'm going to just write. Now, if I wanted to find out what 1 radian was, how could I go from here to here? Divide by pi. And if I did the same thing on this side, I would get that 1 radian is exactly equal to 180 degrees divided by pi. So we had said it was a little bit less than 60. Now we can go to our calculator. $57.3. So when we squished that triangle down, it actually changed that angle to be 57.3 degrees. And similarly, if you wanted to figure out what 1 degree was, well, I could go from here to here by dividing by 180. Same thing on this side, I'd have to divide by 180. And so we get pi over 180 radians is equal to 1 degree. So your textbook has the official definition of a radian as well. So if you like highlighting things, I should learn that my highlighter stopped working well. Here we go. Highlighter, there. In a circle with radius r, and central angle with a measure of 1 radian is subtended by an arc with length r. In other words, when the arc length is the radius, that angle is 1 radian. And on your next page, where they have this radian measure, that one in the green box is the one that you're going to be able to remember the easiest. That you know in a whole circle that there's 360 degrees. And you know that the circumference of the whole circle is 2 pi r, so there's going to be 2 pi radians in that circle. Now, from there, it's really easy to determine that pi radians is 180 degrees. And one of the mistakes that students make a little bit later on is they start saying pi equals 180. Pi is a number. What's it equal to? It's equal to 3.14. Is 3.14 equal to 180? No. But if I say pi radians, I can say that's equal to 180 degrees. The units are important. Okay, another example. Is 1 equal to 12? If you say yes, I'll give you $1, you give me $12 back. We'll be good. No. But if I say 1 foot is equal to 12 inches, then they're the same. So if we have our units in there, it's important. So pi radians is equal to 180 degrees. And then we saw before how we could get these two in the purple boxes. That you could divide by pi to get 1 radian, or you could divide by 180 to get 1 degree. And those ones in the purple box are really helpful for converting back and forth between different measurements. If you had to change 7 degrees to radians, I'd use the second one and multiply both sides by 7. And I'd find out 7 degrees is 7 pi over 180. If I wanted to find out what 3 radians was, I could use the first one. Multiply both sides by 3, and I'd get 540 degrees over pi. So those two are useful for changing back and forth, and we're going to be doing a lot of converting. The problem with the ones in the purple box is that they're very similar. Can you see yourself mixing them up? One has 180 over pi, the other one has pi over 180. So we'd have to come up with what are ways that you could remember them easily. Me personally, I always start with the green and the blue one, because it's really easy to go from the blue to the purple ones and not make a mistake. And it's really easy to go from the green, that you know that there's 2 pi radians in a circle, there's 360 degrees in a circle. It's really easy to get the green and the blue from memory, because it just sort of makes sense. And then you can get the purple ones after that. Now to connect stuff that we did yesterday or the other day, we had calculated our arc length in degrees. We wrote this down earlier today. That is just a proportion of the circumference. We can now also do the same thing in radians. And in radians, what am I going to put instead of 360 on the bottom? It's still a proportion of the whole circle. It's going to be 2 pi on the bottom. And my circumference would still be here. Now, I mentioned to you when we did the arc length in degrees that I like this formula like this, not simplified, because it means something. It's a proportion of the whole circumference. Okay? The arc length in radians is the first formula on your formula sheet, and they do simplify it. It's because they simplify it because it's just too tempting not to simplify it. What's going to happen with the 2's? They're going to cancel out. What's going to happen with the pi? It's going to cancel out. And this formula simplifies just down to theta r. The arc length in radians formula, this is on your formula sheet. The degrees one is not. So you can use both of them, but if you're using the degrees one, you have to pull it up from memory, which it's not hard to do because it's a proportion of the circumference. If you understand the idea, then the formula just naturally falls from that. But the arc length in radians is on your formula sheet. So I'm going to give you your formula sheets now. Given that theta is 170 degrees, determine its measure in radians. So for part A, we know that 1 degree is pi over 180 radians. If we wanted to find out what 170 degrees was equal to, we'd have to multiply by 170. So on this side, we multiply by 170 as well. And again, you could reduce 170 over 180 to be 17 over 18. It's not wrong to reduce it. However, you won't lose marks if you don't reduce it. If you left it as 170 over 180 pi, that's perfectly fine. Okay? The other thing that's interesting with degrees and radians, you know the sign for degrees? Okay? Notice I've been writing radians every single time. Sort of like, oh, that's kind of annoying to write all those letters. So you're wondering, well, what is the symbol for radians? Okay? How should I write, if I wanted the angle to be 170 pi over 180, how do I show that it's radians? Just like that. With no symbol, this is going to bother some of you, it means radians. That's why maybe in previous years, maybe you lost a half a mark on a test because you did a triangle and you labeled this angle as 30 degrees and you forgot the degree sign. You didn't know at that time, but that actually means 30 radians then. 30 radians is a lot of degrees. We could figure it out, right? One radian is equal to 180 pi degrees. So 30 radians would be 30 times this. Type that into your calculator. 5,400 divided by pi. Oh my goodness, 1,718 degrees. So you didn't know it, but when you labeled an angle as 30 without the degrees sign, you were labeling a huge angle without knowing it. So that degrees sign is really important. And in radians, no sign is necessary. And this is probably one of the reasons why students, right, 180 degrees is equal to pi radians. It's one of the reasons why they start to think pi equals 180. It's not. 180 degrees equals pi radians. But pi is still 3.14. So we've got our exact measure. This would be an exact measure. If we wanted it as a decimal, we would have to type it into our calculator. 2.97 to the nearest hundredth. Part B. I'm going to start to teach you how to think in radians. Because right now, that's going to be hard. Because your whole angle life, you've probably dealt in degrees. And now we have to start thinking in radians. So we're given theta is equal to negative 12 pi over 11 radians. We need to sketch that angle in standard position. So for part B here, we know that standard position starts from the positive x-axis. And we want to go negative 12 pi over 11 and be able to draw that in the right quadrant. First of all, the angle is negative, so just like degrees, does it make sense that we're going to be going in the clockwise direction? Thinking in radians, all the way around is 2 pi. So here, you're starting at 0, but if you went all the way around, it would equal 2 pi. Halfway around would be pi, 180 degrees, pi radians. If we are going negative 12 pi over 11, can you see that your fraction is a little bit more than 1, 12 over 11? So I'm going to need, this would go negative 1 pi, and I need to go negative 12 over 11, which is a little bit more than 1. I'll need to go probably about this much more. Now, how did I know about how much more? Well, this 11 is on the bottom, meaning that pi, halfway around the circle, pi radians, has to be divided into 11 equal sections. Can you visualize half of this circle divided into 11 equal sections? And does this part right here look like approximately 1/11th? I'm just estimating it right now, but that's the kind of visualization you would need to do. You'd have to put things into proportion. Now you could change, and many of you will want to do this at the beginning. You're going to say, can't I just change negative 12 pi over 11 to degrees? Because I know that 1 radian is equal to 180 over pi degrees. And so if I change this to degrees, I would have multiply by 12 pi over 11, 12 pi over 11 radians. I'd have to multiply this side too by 12 pi over 11. So I'm going to write that out right now. 180 over pi multiplied by 12 pi over 11. And when simplifying this, can you see that the pi's are going to cancel out? And so on the top, I'm going to get 12 times 180 over 11. If I type this into my calculator, (196.4 degrees). And I reread this, and it is to the nearest tenth, so I've rounded correctly. Yes? Yes, sorry. We need negative. There would be a negative here, a negative there, a negative there, negative there, negative there, negative there. Thank you. So negative 196 degrees. And we're also going to make a note a shortcut for changing from radians to degrees if there's a pi involved. So notice I have negative 12 pi over 11, and I'm wanting to change that from radians to degrees. Take a look at the work that we did and see if you can figure out a shortcut. So, I mean, here we did all the work, but can you see how you could get to this step quicker? If a pi is involved, does it make sense that the pi's will always simplify? There's one on the top and one on the bottom. And then, what's in place of the pi? 180. So if a pi is involved, the shortcut is you can just replace pi with 180 degrees. Because you see how negative 12, 180 over 11? And it was negative 12 pi over 11? And it kind of makes sense because pi radians is equal to 180 degrees. Finally, part C says change 7.5 radians to degrees. We can't use the shortcut in part C because there's no pi involved. So we'd have to go back and say, I know that 1 radian is 180 over pi degrees. So 7.5 radians would equal, well, have to multiply by 7.5, have to multiply by 7.5. On my calculator, 180 times 7.5, 1350. So if I wanted to write an exact answer, I'd write 1350 over pi degrees. If I wanted to do an estimate to the nearest tenth, $429.7 degrees. So I'd like you to try questions 4, 5, and 7 and start getting your brain wrapped around working with radians.